continue the discussion about the oxidation of silicon. Okay, we start with the Dylan-Grove model to explain the oxidation behavior of silicon, and we have two constants related with the oxidation process in the silicon. One is the parabolic rate constant, which is related to the diffusion coefficient of oxidant inside the oxide, and linear rate constant, B over A, which is related to the surface oxidation reaction of the silicon. Okay? Now, today we are going to discuss about the charges exist in the oxide. The oxide is an insulator, so that differently from the metal, the charges are very important inside the oxide. And in the note, the four important charges are explained. Okay. One is the interface trap charges and the fixed oxide charges and oxide trap charges and mobile ionic charges. There are four important charges, and for each charges has been explained in the text, but let me just briefly introduce the four different charges. Okay, the first silicon and the silicon oxide and interface trap charges is the charges in the silicon side at the vicinity at the interface of silicon and silicon oxide. Okay, that is the interface trapped charges. And the charges which just corresponding to this interface trap charges, we call that fixed charges. And this fixed charges is in the silicon oxide, okay, QF. So the amount of fixed charges and interface charges is about the same. And the other trapped charges, immobile trapped charges, it's just the charges which is trapped, really, as it the name is, as it is called. It's just trapped in the oxide, so it is not moving at all. And we have another charges, mobile charges in the oxide. And the mobile charges here is mobile at elevated temperature, at high temperature. Of course, at the room temperature, excuse me, at room temperature, the charges is not that mobile. But when you elevate the temperature, like during the oxidation, the temperature is about 1100 degrees centigrade or 1000 degrees centigrade. At that high temperature, this mobile charges are very mobile, see, and typically the sodium, which has been come from our sweat, okay, sort of contamination, and hydrogen. These two elements, potassium and so forth, they are very mobile at the high temperature. So this mobile charges is going to be implemented in the oxide during the oxidation process at the high temperature, okay? And it affects the electrical properties of the transistors. And this oxide, when you think of the transistors, something like this is the gate oxide, okay? And this is the gate, and the source and drain, and this is the silicon. Now, According to this definition, what we are going to have here at the channel on the silicon side, we are going to have in-phase trap charges and the corresponding fixed charges on the oxide. We're going to have the charges like this. And these charges, of course, it affects the electrical properties of the transistor, especially the threshold voltages, mobilities, and so forth. Okay, and again, the trap charges here and the mobile charges here also affect these properties as well. Okay, now these trap charges and mobile charges, we do not want this, so we want to minimize this during the process as much as possible. But about the fixed charges and interface trap charges, it just happens because of the defects. Interface is kind of defects, right? We are going to have silicon-silicon bonding, covalent bonding of this, something like this. But at the interface, where we are going to have a silicon oxide here, then the top silicon is going to bond it with the oxygen, something like this, okay? And so this silicon is different from this silicon, and this is oxide side, we are going to have fixed charges, and this silicon side, we're going to have negative charges, which is called interface trap charges, something like that. So we cannot avoid this. We can minimize this by using the surface. Well, as you can see, the charges, amount of charges should be related to the amount of silicon and the plane, right? So if you have 1, 0, 0 plane and 1, 1, 0, and then a 1, 1, 1 plane, we have atomic density, something like this, right? So as far as the interface trap charges are concerned, we are going to have interface trap charges at 1, 0, 0, much less than interface trap charges in the 1, 1, 1. Okay? Because we are going to have a less densely populated silicon atoms at 1, 0, 0. So we have a less chance to have these defects in 1, 0, 0. Okay? And this is why in the MOS transistors, the 1, 0, 0 silicon wafer is preferred than the 1, 1, 1 silicon wafer. We prefer the 1, 0, 0 silicon because we have less interface trap charges in this case. Okay? That's a very important fact. But in bipolar transistors, this interface is less important in the bipolar transistors. In bipolar transistors, as you can see, we have emitter, base, collector, something like this, okay? That is the bipolar transistors, okay? Here we do not have this silicon oxide and silicon interfaces in the bipolar transistors. So in bipolar transistors, we use 1, 1, 1 wafer, okay? But in the MOS transistors, we do not want large interface trap charges, so we are using 1, 0, 0 silicon wafer for the MOS, the transistors. And that is the reason. And this is inevitable. So we have to find a way to minimize this interface trap charges, and there is a way to minimize this. What we do is we do hydrogenation. We call this hydrogenation. What you do is at the temperature 450 degrees centigrade, about just 30 minutes is enough to hydrogenate the interface. We put the transistors after all the process. We put the transistor in the furnace and maintain the temperature 450 degrees centigrade, and then we just cook it for 30 minutes. And then we're going to see later in the masking properties, the hydrogen can penetrate this oxide very easily. It is very mobile. Hydrogen is very mobile. So hydrogen, which is H plus, proton is H plus, is going to annihilate this negatively charged interface trap charges. Okay. It compensate or annihilate the interface trap charges so that you can decrease the interface trap charges. If you decrease the interface trap charges, then the fixed charges is going to be decreased as well, accordingly, because this fixed charges are about equal in amount to the interface trap charges. So this is what we call the hydrogenation process, and is going to be carried out at the end of the process, at the end of the fabrication process. And that's very important, okay? Okay, and then, note, we have to move to the next section where the advanced topics, okay? Before advanced topics, it has some explanations of fixed charges and interface trap charges, and this is, I like this figure. Okay, interface trap charges and fixed charges I explained. And by nature, as far as you have a different layer silicon oxide on top of the silicon, then you're going to have a defect somehow, and those defects we cannot avoid that. And then that interface charges and fixed charges are related with the defects, that interface. So we have to do the hydrogenation process to decrease the amount of interface trap charges. Okay, and experimental results has been shown. Here there is a lot of explanation about the threshold voltages in the MS transistors here, but the details of this is going to be discussed in the other class. So I'm not going to go deeply on this, in details of this, but this is the result, and you can see the fixed charges, the charges in the oxide are going to affect the threshold voltage of the device. So at least you have to know how much the fixed charges you have in the real industrial practice, okay? And it is not good to have the fixed charges and the charges in the oxide, because it is going to affect the threshold voltage, but you cannot eliminate all the charges. You have to live with some charges in the oxide to some extent. But the important thing is you have to have that charges uniformly throughout the wafer. Otherwise, you have your threshold voltages of your transistor is going to different device by device, and you cannot use it in the industry. So if you cannot eliminate all the defects, the charges in the oxide, you have to find a way at least to make it uniform, okay? And that is very important in the industry. And that's why we want to keep the clean room in the fabrication processes. Okay, this is just what for your reference, so we just skip it. Now, the advanced topics. 4 topics we are going to discuss in the advanced topics. And the first one is the dopant redistribution. Dopant redistribution means when you have a silicon surface, okay, and then with the diffusion process, you dope the silicon surface with a dopant to, let's say, uniformly, you doped the silicon with the dopant atoms, okay? Dopant, typical dopant atoms, boron, arsenic, phosphorus, antimony, things like this, okay? And then what you do is you elevate the temperature like 1,000 degrees centigrade or something to get a silicon oxide through these reactions. Okay, and then you're going to have a silicon oxide on top of this silicon. Now, this dopant is going to be implemented cooperated into the silicon oxide. Okay, so that's what we call here in this text redistribution of the dopants. How the dopant atoms is going to be incorporated into the silicon oxide. Okay, and that's very much dependent on the value segregation coefficient. We have equilibrium segregation coefficient K naught in a Czochralski crystal grain, right? Here we have M, which is going to be called equilibrium segregation coefficient. And that equilibrium segregation coefficient is going to be the concentration of silicon, the dopant concentration in the silicon over dopant concentration in the silicon oxide. And this silicon oxide is going to be grown on top of this silicon. Okay? Now, if the value M is less than 1, then we are going to have depletion of the dopant atoms. This is the silicon and silicon oxide. And M is less than 1, then we're going to have depletion of dopant in the silicon. Originally, before the silicon oxide, we have this much dopant concentration, and by growing the silicon oxide on top of the silicon, then the dopant atoms is going to be incorporated into the silicon oxide, so that it's going to some depleted zone, okay, like that. Now, if we have the M greater than 1, then what we're going to have here is that accumulation of the dopant atoms in the silicon if M is greater than 1. Okay? So here we have the silicon oxide, the dopant atoms, and at some depth from the silicon oxide interface, we're going to have accumulation in this case, accumulation. Okay, why is this important? Now, if you think of the MOS transistors like this, and then this is the source and drain, this is the silicon. Now, if you have P-type silicon substrate, and then you're going to have an NMOS, so that the source and drain is going to be doped with N+, okay? And then somehow, if you grow the silicon oxide on top of this, let's suppose you dope the source and drains like M plus like this, and then you grow silicon oxide here, thermal oxide, something like this. Then what's going to happen is that at this interface, in the M plus case, where the phosphorus, the M value is about, phosphorus M value is about 10, okay? It's much greater than 1. In boron case, the M value is about 0.3, okay? It's less than 1. So if you have phosphorus doped area like this, locally, and then you grow thermal oxide in the later process, then at this interface, what's going to happen is that you're going to have accumulation of the phosphorus at this silicon interface, right? What happens if you have an accumulation like this? Then this accumulation may exceed the solubility limit. Solubility limit of phosphorus in the silicon, which will make the formation of precipitation, the second phase of the silicon. And if you have a precipitation, then those precipitates are not going to be related to the resistance and whatsoever, okay? It's a totally different material itself. So this precipitation is not only the defects, but also it is going to decrease the resistance, increase the resistance, decrease the conductivity of this material, even though after the heavy doping of phosphorus. Those phosphorus is some of the phosphorus is going to be consumed, you should say, consumed to make the precipitation like this. So this precipitation is not good in the actual practice, okay? Now what happens if you doped this source and drain with the borons? You are going to have a depletion because the M value is less than 0.3, right? Then if you have a depletion like that, then of course we are going to increase the surface resistance of source and drains because you have a less amount of borons that you put during the pre-deposition and drop-in. So in a modern transistor fabrication, we do not want to grow oxide, especially thermal oxide, after the doping. We want to make a thermal oxide before, and it is very much preferred, and it has a theory behind. We want to grow the oxide before any doping process, okay? So dopant distribution is very important. And in the note, one thing you should notice is that this is the boron case, M is less than 1, and then you can see the depletion of the boron in the silicon side, right? But look, if you have a situation that the boron is diffusing in the oxide much faster, okay, much fast, then what's going to happen is that this depletion is going to be enhanced, promoted, because you have a high diffusion coefficient of the boron. And it turned out that if you do the oxidation in the hydrogen ambient, like in a pyrogenic or H2O, wet oxidation case, then that hydrogen will promote the diffusion of a boron in the silicon oxide so that you're going to have a situation like B, Okay, even though the M value is both A and B is the same, less than 1, but if you have a fast diffusion in the oxide, then you're going to have a more depletion in the silicon of the dopants, like that, okay? And that can be done by boron with H2 ambient, okay? And in the case of phosphorus, arsenic, and N-type, any N-type, we have the accumulation like this. And this is the case of a special case, not really happens in practice. But for example, the gallium case, you have a very fast diffusion in the oxide, so that instead of accumulation, you're going to have depletion, because a large amount of dopant atoms is going to be deprived, you should say, incorporated into the oxide in this case, if the diffusion process is very fast in the oxide. All right, let's move on to the masking properties. And this is the phenomenological thing. No, it's we can do the calculation by knowing the diffusion coefficient of the impurities in the oxide, but it's very complicated equation we have to solve. This is just a phenomenological observation. Now, for sodium, very fast, and hydrogen is even faster than the sodium, okay? The gallium is relatively fast, something like that, okay? The hydrogen, you can see very high diffusion coefficient in the oxide. So these are not going to masked by the silicon oxide. These elements are not going to be masked by the silicon oxide. And phenomenologically, we got this result, and the way to read this plot is that this is the thickness that you need to mask these impurities at these temperatures to this diffusion time. Okay, for example, if you do the diffusion at 900 degrees centigrade, and the diffuser is, the dopant is a phosphorus, then if you carry out the diffusion time at 10 minutes, then this thick silicon oxide is needed to mask the diffusion of the phosphorus. This is the way how you read this, okay? If boron case, at each temperature you have a different, you need a different thickness of a silicon oxide to mask the boron diffusion, of course. Okay, the next topic is oxidation rate. Oxidation rate is related to the dopant concentration. For example, if you have a phosphorus, okay, N-type dopant, phosphorus, you know M is about 10, so that you have a accumulation of the dopants at the interface, and this high concentration of dopant will affect the oxidation rate. As a matter of fact, this concentration, phosphorus concentration, enhance the oxidation rate, okay? That means if you have a silicon, here's something like this, okay? And then you have some area where the phosphorus doped. Okay, when you say P plus, then it's P type. So let's say if you have an N plus and the phosphorus is doped, something like this, and you grow oxide, okay? then what you are going to have after the oxidation of this silicon is that you have a very thick oxide here and then thin oxide, something like this. Okay, that is the dopant effect. So if you have a CMOS, for example, and you're going to have a field oxide, it is not a scale at all, but when you have a CMOS like this, okay, and then you have a well here, and then P substrate, P-type silicon, and then you have a NMOS here, and then you have a N well, and then P plus here. Okay, this is the typical picture of the CMOS, which is commonly used in the modern VLSI process. Okay, you have a P-type PMOS and NMOS at the same time on the silicon wafer to suppress the standby current. That is the CMOS. Okay, in doing this, some part of your silicon is going to be, it should be doped with phosphorus, and some part, the boron has to be doped, okay, for the PMOS and NMOS. And so we need some extra mask to make this P-type and N-type. But if you take advantage of the dopant effects or something like this, then only the phosphorus shows a different thickness of the oxide. What you can do is you are going to dope the phosphorus something like this before you make this thing at all. You dope this with the phosphorus and then do the oxidation, and on top of this, only on top of this, the oxide is very much thicker. The oxide grown here on top of this phosphorus is going to be thicker than in the other areas. Okay, and then without any extra mask, you can form the PMOS here by using this extra thick oxide as a mask. Right? So this is how, if you take advantage of that fact, you can eliminate one mask step. And typically 7 mask steps are needed to form a CMOS. And if you can reduce to just one mask step, then it's related to cost tremendously. And that's very important. So one time when I worked in the Fairchild, we work on this process to eliminate, to skip one mask step very intensively, but finally it is not that reliable, so we just gave up. But I remember we have worked on this seriously, okay? And then the section here we're going to discuss is about dopant effect on the oxidation rate. How it is affect that. This is the experimental results. At elevated temperature 1100 degrees centigrade, the phosphorus concentration does not really affect the oxide thickness, as you can see here. But if you go down, lower the temperature to 800 degrees centigrade, now you can see very much a different oxidation rate from F to A, okay? This is A, and F is just to increase the amount of phosphorus doping. So at low temperature, we have learned that at low temperature, the surface reaction is important, right? At high temperature, the diffusion process is important. So at low temperature, the dopant sensitivity to the dopant concentration of the oxidation rate is very serious, okay, considerable. At low temperature means this dopant may affect the surface reaction at the oxide. We can see that from this plot. But on the next experiment, you just distinguish the B of A linear rate constant, the surface reaction constant, and the diffusion related constant B. And the x-axis here is the dopant concentration. And as you can see, if the dopant concentration is well over 5 times the 10 to the 19th, then this the dopant diffusion related constant is not changing much, but the surface reaction constant is going to exponentially increase. So what you can see here is that the enhancement of the oxidation rate with the high concentration of phosphorus is really come from the enhancement, increase in the B over A constant rather than the parabolic rate constant, B. Okay? So, from this results, we can see that the dopant concentration affects the surface reaction, not the diffusion of the oxidant. And that's why we have enhanced diffusion of the oxide, okay, oxidation rate. And finally, let me talk about the HCl oxidation. This is what really happens in the industries. Okay, in the industries, we do not use a dry oxidation or wet oxidation or pyrogenic oxidation. We usually use the wet oxidation plus this HCl gas. What happens if you flow the HCl gas and the oxygen? Then what we can have is that it's very much like wet oxidation. We form water here, and then we have a Cl2 gas as well. And it turned out that the Cl2, Cl minus ions is going to be accumulated at the silicon oxide side of the silicon oxide and silicon interface, as you can see here. And this is the location where the fixed charges, which is the positive charges, okay, are located right at here. So which means that this Cl minus, which is accumulated at the interface, is going to annihilate the fixed charges, which is a positive, so that it also decreases the amount of interface trapped charges. So that's why it is preferred in the industries. Not only enhance the growth rate, because the dry oxygen is going to form water, like a wet oxidation, but also it can annihilate decrease the number of fixed charges, correspondingly the interface trap charges, where the Cl minus ions accumulate at the silicon oxide interface. That's beautiful, isn't it? Okay. So here's the possible region speculations. With the HCl oxidation, you're going to have water there. So we are going to have a good enhanced oxidation rate, and Cl minus ions near the interface, so that it'll affect the B array. Cl minus also affect the B. And silicon etching by Cl at a high temperature. This is not a good thing, good effect. But it may have a silicon etching because the silicon chloride is a gas form which is going to be a byproduct after the etching of silicon. Well, actually it is not that bad because we can have a clean surface in the oxidation. So we cannot say total bad effect in the silicon etching. So that is the hypothesis. There's a speculation that we can see. But in real practice, okay, the HCl oxidation really happens in the industries. Well, here's a summary. Silicon orientation affects the B over A, not B. And if you have multiple steps, then you know how to calculate the final thickness, okay, after the multiple processes. HCl, that's what happens in the industry really, and the doping will affect the B over A to enhance the oxidation rate. Okay, and in the note here we have some advanced topics just to follow as a chapter 7. We are not going to discuss about this chapter 7. It's going to be discussed in the other classes in the graduate course, okay? And you just skip the chapter 7. So next week, on Monday, we're going to discuss about the ion implantation, which is chapter 8 on page 201. All right? Okay. Have a nice weekend. I'll see you next week.